Okay, so I'm not sure what happened to Mark, but and also I'm wondering why is it not showing me? Because it's kind of useful to know if one's head's at least in the picture.
You know, your middle center.
That's good to know. Let's see here. Manage participants. Okay. All right. Yep, who knows? Alrighty. Okay, let's jump straight in.
Yep.
Okay, so you're seeing me all right. Let's see if I move this. Hang on. Maybe there's another thing. There we go. Okay. Alrighty. Okay, so we had looked previously at the synchronous generator when it is supplying an individual load.
Yeah.
Okay, and the key things when we analyze these things is don't forget first that we want to draw everything as one phase, as if it was essentially a star connected system. So invariably your three-phase system is specified by line voltage, so you're going to want to divide that by √3. And if the system gives power or parent power, whatever it is, it's going to also probably give it in terms of the system as a whole. So divide that by 3 simply if you're wanting to get the power per phase or the parent power per phase. And then really that E there was the system or the terminal, sorry, that there, if you were supplying a particular load, yeah, that's what the load was going to see. But in order to see that, you have to actually generate this voltage internally, that's the induced voltage E0, so that when you lose, once current flows, you're going to lose some voltage in the synchronous reactance. It's like an internal resistance, but it's a reactance. So we're going to lose that. So the load will see this even though you're generating that internally. So that was here. And of course that E0, yeah, so E0 is a positive vector there, minus something leaves us with whatever we have left across there. And the beauty is that we can control this E0 because simply by adjusting this exciting current, and we can see the effect of that on that no load saturation curve, which I won't jump to now. But there was a graph showing an exciting current versus an induced voltage E0 for a particular generator. And by simply playing with that, we can force any E0 we want to be established within limits. Of course, there will be saturation at some point. And in doing so, we can then achieve whatever voltage we want over here. So when you analyze, don't forget to convert to per phase, and then key things again, summarizing. The current here is dictated by the power factor of the load. The load itself sees that voltage and it sees that current. So that difference between that voltage and that current is purely dictated by the power factor of the load, independent completely of the synchronous generator. So that fixes the angle of the current. The size of the current gets dictated by, well, either you might have a Z of the load, or perhaps the load's being given to you like this, where they specify it as a certain amount of MVA, or even a certain amount of megawatts or kilowatts. So depending which they're doing, they just, obviously you can, either way, you can get this amount of current for any given scenario, whether they quote it as MVA or kilowatts, or even a resistance, or rather an impedance, which would have a natural angle. Either way, you can get that angle and you can get that amount of current. Once you've got that amount of current, that same current that the load sees has to flow through the synchronous reactance. If we look at our little diagram, what the load sees, the synchronous reactance sees. So if you force a certain current through there, you'll develop a certain voltage across it simply by, it would normally be V equals IR, but now it's V equals IX, because it's a reactance. Whoops. So that will define the size of this. So the load determines how much current you have based on seeing that voltage and the characteristics of the load. Once you've got that current flowing, it will force a voltage to develop across the synchronous reactance proportional. This voltage is I times X, or XS, which is the synchronous reactance. And once you've got that drawn in that place, that then enables you to say, I've got this terminal voltage. I know now the size that I need for this guy. I'm going to draw him in there, and I'm going to find then, typically you're using that to actually find this vector. So you don't know that vector. You're arriving at it from saying, I need this terminal voltage. That's my EX drop. Therefore, this is what my vector needs to be for E naught. And then you go and see what size it is, and you go back to your no-load saturation curve, and you come down and see what exciting current is required to make that. When you actually analyze these things, the cos rule can be your friend here. The cos rule says any triangle like this one, this squared plus that squared, no, sorry, that squared is this squared plus that squared minus 2 times that side times that side times the cos of this internal angle over here.
Yeah.
Okay, so of course the trick then is to just see what is this internal angle. So if you extrapolate this line over there, then between the horizontal and that thing will be the same as that, between the horizontal and that. Okay, and then 180 minus this thing to the horizontal will leave you with what's in the middle over there. But of course, finding this one itself, EX relative to E, well, how do you find that? We know it's 90 ahead of this one. So if you got that angle, then 90 minus this theta will leave you with this bit over there. Okay, so constructing that is not too bad. This one, similar scenario, but this is with a capacitive load, where it actually turns out that E naught can be smaller than the terminal voltage because there's a bit of a partial resonance happening. But same procedure for working that out. You can also use a more of a, you can write these things as, we'll see it later in the section on the motors. We can just do it more from a pure maths point of view, where you write this vector as a certain magnitude at a certain angle, and you write the synchronous reactance as being defined by Jx, and then we can work from there. But we'll come back and look at that. You can also construct it with a bit of trigonometry if you're feeling inspired, but the cos rule should be the simplest.
This is really similar to working out line losses in a transmission line, where your E0 would be your sending, the voltage that you send, and your E would be the voltage at the end of the line.
Okay,
and
cool.
Your angles are your losses. Yeah, it's really
very
much similar.
Very much the same. Did you do that with Bujanga?
Yeah.
Okay, cool. So that means 2 birds with 1 stone there. Should be easy. Okay, so have a look through these little examples, but these examples are all, they're sort of special cases. Like this one is for a load that has a power factor of 1. So in other words, we don't have the current at an angle down here. You can see my mouse, eh?
Yeah, gotcha.
The current is horizontal. So that makes the maths a little bit simpler, because now you've got a And 90 away from that would be straight up. Now you've got a right angle triangle, and you can do some simpler trig on there.
Yeah, that's a good example.
Yeah.
It's good in the exam. Yeah.
And this one here, similar story, but now all the current is perpendicular to the E, because the load is only a capacitor, not a resistor. Okay, but the more general case is the diagram that we looked at, where your load is going to have a bit of a power factor on it. Could be leading, could be lagging. Okay. Discuss regulation curves. Yeah, we're going to talk synchronization of a generator. So we'll go over this in some detail in the block course, but basically you've got to, before you actually engage circuit breakers linking the generator onto the grid, you've got to get everything just right. So it's got to be rotating at just the right speed. You've got to have excited it so that the voltage that it's producing is just the same as the system that you're about to link it onto. There needs to be the right phase sequence. And basically, when everything is just right, if you have the right measuring tools, you can see when it's all just right, and we'll look at that when we're on campus. We don't have the synchroscope, although one can use that. We have a system with some light bulbs where the lights will pulse, and if there's a voltage difference across the terminals, they'll be on. But if the voltages across the terminals are matched perfectly, and one side's the grid and the other side's the generator, the bulbs will go dimmer, 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 and then we'll know we can flick that switch.
Yeah.
Okay, so we'll do that together. And
we at the start of last year, I installed a generator, or done an upgrade to a generator, and they still use that system.
Okay, with the light bulbs?
It's supervised by electronic relay, but for simulation's sake, they still have that system running.
Okay, cool.
1920s.
1920s. Okay. Nothing's changed. Well, some things don't change in a hurry, huh?
Yeah.
Ohm's law is not going anywhere.
No, apparently not. Those poor apprentices.
The poor what?
Apprentices or trainees.
Why is that?
Oh, they have to study Ohm's law.
Oh, right. Oh, yeah. Shame. Yes. Okay. Right. Then once we're actually online with our generator, then we can play with basically two parameters. One parameter is the exciting current. And as the book goes on to say here, that actually doesn't change any real power. So we can have our, it'll change the amount of voltage E naught, the induced voltage. It'll change that amount, and it can make it bigger or smaller than the grid voltage. And it can result in reactive power being transferred either to the grid or from the grid. So it's acting, the one will be acting as the generator will see the grid as a inductive load. If it's delivering reactive power, that's the way we'd normally term it. And if the generator is seeing the grid as a capacitor, then it's actually, the grid is feeding reactive power to it. That's the sort of positive and negative way that it's normally, if it's a capacitor, it's receiving reactive power, and if it's an inductor, it's absorbing it. Whereas real power, we have to actually, somewhere in the line, we can imagine there's got to be some torque. So you've got a turbine on the shaft here. That turbine trying to force this generator around. If there was no torque and the shaft was spinning freely, then we'd have no power transferred whatsoever. Yes, the steam turbine would have to operate against friction, but there'd be negligible torque required. So until you actually apply torque to the shaft, no power gets transferred. So the system will, what they call, float on the line, where it's all connected but there's no power transfer. It could be reactive power though. And then when you try and force the generator via the steam turbine, or whatever kind of turbine it is, you're trying to make it go slightly ahead of the stator in terms of where the flux is, then you end up causing an angle between the E naught and the E. So let's just have a look at this, what the picture of this looks like, just to get a feel for it first. Here. Okay, so under normal situations, if there's no torque and everything's just spinning freely, the rotor is spinning, but there's a rotating magnetic field produced in the stator because the thing's on the three-phase line. So like we had for an induction machine, you've got the peaks and dips of the three phases causing a rotating magnetic field. And as that field rotates, if this magnet lines up with this pole at all times, then there's no torque and the turbine just spins freely. If, however, you try and accelerate the turbine slightly relative to the stator, then there's some attraction forces which develop. There's kind of a south pole over here and a north pole over there, and we're trying to turn it this way. And if we succeed in making this north pole a few degrees ahead of the corresponding south pole on the stator, then we're trying to drag this thing around with us. That's when we create a so-called torque angle, which makes the induced voltage E naught actually lead slightly in front of the E. So the E is what is seen here, because E is the grid voltage. E naught is what is induced by, well, yeah, they're kind of together. E and E naught get superimposed in here. E is happening from the grid. E naught is happening from this induction process as this magnet moves around. And what will happen is, as you try and open the steam turbine's valve, this will creep ahead and creep ahead, rotating all the time, but eventually it will settle at a certain number of degrees where each pole is slightly ahead of its corresponding pole on the stator. So every north is a corresponding south. Somewhere else there'll be a south on the rotor with a north on the stator corresponding, but they're all, one's just slightly ahead of the other. So what that does, the actual relationship between the so-called mechanical angle, which you could measure physically on the machine, if you had some way of knowing where the rotating magnetic field pole was from the sum of the three phases, and some way of measuring where the actual physical rotor was, you could actually know what that angle is, but it's easier to see it electrically. But there's a relationship that bears in mind the number of poles or pole pairs, which then relates this angle alpha, the mechanical angle, to another one called delta, which is the torque angle. And then going back up here, what that torque angle does is what that torque angle does is it forces the induced voltage E naught to be slightly ahead of the line voltage, the grid voltage. So that this is happening at a slightly earlier point in time than that, because the rotor has been forced ahead of where it would naturally sit. So it would normally naturally sit that all the norths and souths lined up and they just move together. But now the rotor is going to be tugging ahead, so to speak, of the rotating magnetic field. So when it moves ahead like that, there's a certain number of electrical degrees delta, which will correspond to the number of mechanical degrees on the actual physical machine, where there's a relationship that takes into account the number of poles or pole pairs. At the end of the day, the electrical one is what we want, so one sees it here that there is the induced voltage over there and the grid voltage over there. An important thing to note here in this particular case, they happen to have adjusted it so that we have 12 kilovolts of E naught, the same, in other words, as E. Of because that's the line to neutral voltage. So if we have it like that, then the thing is neither what they'd call overexcited or underexcited. They've made the induced voltage exactly match the line voltage. But because it's ahead of the other one, there is actually a potential difference, and current will actually flow, which we know anyway from a three-phase system.
Yep.
All the voltage phases are the same size, but because they're out of phase, you put a resistor between one line and the other, and some current will actually want to go through there because they're not in sync. So that difference over there, if you subtract again that number or that phasor from that phasor, the difference that you get there would be this EX. Again, from a circuit analysis point of view, you've got a vector here from a minus to a plus. Kirchhoff's law around here, that would be like a rise. And if a rise was here, it would force current this way. That would be a vector with the positive end here and the negative end there. So the vector would be pointing to the left. So it would be a drop if we're going around like that. And then the infinite bus here, if we're feeding current into it over there, we're assuming that this is a more positive terminal than that one, and we're forcing it in, like charging a battery. You'd be forcing a current into the positive terminal to charge it up. If it was the other way around, it would be busy discharging. So if you do rise equals drops around here, you've got this vector, and this vector, and it will work out that that rise is equal to that drop plus that drop, which boils down to the difference of these two being the amount that is being seen across here. So if we know this angle, because let's say we can measure the mechanical angle, or maybe you've got some electronics on the system which are measuring that phase shift, we can actually then work out what this number would be. Once we know where that vector would be, we've got it in terms of size and in terms of angle. Then the next thing is that we know that the current in this reactance, because it's a pure reactance, the current must be exactly 90. So the angle between that thing there and that thing there must be exactly 90, which means once you know where this one is, you now know where the current is. And once you know where the current is, you can now see how much power and how much reactive power is delivered to the bus, the grid, because the cosine of that angle there between the grid voltage and the current that you're feeding into the grid will give you the power factor. Sorry, so if I multiply that R by that E times the cosine, I'll get the real power being delivered to the grid. And if I multiply the I and the E by the sine of that angle, that little angle between the two of them, then I'll get the reactive power. And if I just multiply the two of them, R times E, I'd obviously get the apparent power. Okay, so once you've drawn this vector diagram, you can actually see how much real and reactive power is delivered to the grid. It's a little hard to visualize whether the reactive power, whether we should call it positive or negative. But it basically will boil down to whether the generator is seeing the load as a capacitive type load, or if it's seeing it as an inductive type load. In a case like this, we're looking at the generator. Basically, the I will either be above the line there or below the line by some angle. And the one will be treated as a positive reactive power, and the other one will be treated as a negative reactive power. The way that this is drawn here, I do believe this will be seen as feeding reactive power into the grid. But we can look a little bit later at how to analyze that to see whether we'd call it positive or negative. Okay, but for now, the magnitudes is the important thing. Other things to note, that does not necessarily have to be the same voltage as this. And that thing there is decided by the amount of exciting current that we feed into that spinning rotor. So that vector could be longer or shorter. But again, wherever the vector ends, you subtract this one from that one, get the difference. So this vector could look a little bit different. It could be a bit further back, further forward, bigger, smaller, depending on the amount of excitement. So if we match those two, then we'd call it neither over nor under excited. And normally it would be designed for a certain line voltage, and you'd be then using the sort of rated exciting current and achieving the rated or nominal induced voltage. Don't forget though, once you've done these calculations, if you do find the product of that I times that E, you'll have a apparent power. That'll be just for this phase. So if you want to look at the power for the load as a whole, you must multiply it by 3. There's no root 3's involved because effectively there's already a root 3 in here. This thing here is already not a line voltage. That one is already it's already a phase voltage there. Because our formula would be root 3 line voltage times current times cos phi. So that root 3 normally is handling the fact that it's handling two things. It's handling the fact that there's 3 phases and that there's a root 3 difference between line to line and line to neutral. But in this case, this is already a phase voltage. So simply, the circuit is per phase. So you just take this whole thing and it's happening 3 times over at the same time. So the power is just literally 3 times whatever you get from analyzing one phase. Okay, but yeah, this number here will not be the grid voltage as specified, because when you specify grid voltage, you'll be saying line to line. So you've already divided by root 3 to get this vector here. Okay, because you're analyzing it per phase. All right, so the thing that affects this angle is really how much torque we put on the shaft of the generator, and it tries to pull the rotor magnetic poles ahead of the stator's magnetic poles as the whole thing spins. And we can force that angle bigger or smaller by backing off a little bit of steam or opening up a valve a little bit. Or same thing with water, or if it was a wind turbine, some of the sort of some fancy control systems on there, so I won't go there. But basically, we can control that angle, and the more torque you provide, the bigger this angle will get. The bigger that angle gets, the bigger the difference will be between those two ends of those vectors, which means the bigger the voltage in the synchronous reactance will be, and therefore the bigger the current will be. And the bigger the current is, the bigger the product of the current times the E, so the bigger the power. But technically, of course, the bigger the apparent power, but also the bigger the reactive power. But if you sweep this vector very steep over here, obviously this will tilt a bit further to the left. The current will tilt slightly more upwards. So the cosine, the cos factor might go down a little bit. But nevertheless, the current itself is growing. If you bend this guy further up this way, and you bend him further over to the left, that vector EX is getting bigger, so the current is getting bigger. So the angle changes slightly, but still you will force more real power in, because it's the combination of the size of the current and the product of the current and E and the cos of the angle that dictate the amount of real power. So you've changed one thing, invariably everything gets affected. But effectively you can actually play around with this to get things just as you want them, because technically you can play with the torque angle by trying to force more torque onto the shaft from the generator. the actual turbine, that is, not the generator, the turbine. And you can also vary the exciting current to make this a bigger or a smaller vector. And as you play with those two parameters, you can tweak it so that you can almost independently, in a way, adjust the real power and the reactive power. Not entirely independently, but if you play with the two of them in the right amounts, you can actually come to a point where you can supply a chosen amount of reactive power and a chosen amount of real power. And we'll see in our experiment on campus what happens if you put the torque the other way. So if you have a turbine driving a generator, we could call that perhaps positive torque. What happens if you now actually try to resist that shaft? So you take the turbine away, throw the turbine away, you've got a spinning shaft there with these rotor and stator poles spinning together. If I try and grip the shaft, that's now actually going to become a motor. And I'm going to extract power out of it. My torque direction has changed. So power is torque times omega. If my torque direction has changed, my power transfer must have changed. So we'll see with the same device, we can make it a synchronous motor, where all that'll happen is this torque angle, instead of this vector being up above this line, this vector will now dip below this line. In other words, we're retarding the shaft by gripping on it. It could be with your hands, which I wouldn't try at home or anywhere. But it would be, driving a fan, a pump, a conveyor. So you're actually retarding the shaft. What you'll be doing is you'll be making this phase angle, instead of the E0 leading the corresponding poles on the stator, this thing now will be sitting on the other side here. It'll be happening slightly behind. And the stator poles will be trying to drag the rotor poles around with them, with the rotor poles sitting a little bit behind where they're supposed to be, the stator poles just ahead, dragging it around. So our torque will change, sine, our power will change, and we won't have a generator anymore, we'll have a motor. And the vector diagram will look very similar, but this thing here will be sitting down here somewhere underneath the line, and the EX will also turn around. But again, the more we resist this thing with the load, the wider that angle will actually get. I'll go to the diagram for it in a minute. The wider that angle will get, and the more real power we would need the bigger that EX vector, the bigger the current, etc., making you need more real power to achieve it. So generally speaking, playing with the exciting current mostly changes the reactive power, and playing with the torque mostly changes the real power. But when you do one thing, it affects the other slightly, so you often have to make a readjustment of the exciting voltage if you want to keep things at a certain operating point. Okay, so that's the procedure there. Have a look at this one. This is just showing that torque angle. As we try and push that shaft further and further ahead, we can get more and more power out of the thing. The power essentially is proportional to the torque only, because since it's a synchronous generator, the speed never changes. Yes, that thing could be slightly ahead or slightly behind, depending if it's a motor or a generator, but it still continues to spin at exactly synchronous frequency. It's just slightly out of phase. So the speed is completely fixed. So power equals torque times omega. So omega is fixed. So basically more torque means more power. And you get more torque essentially by increasing, well, more torque makes that so-called torque angle increase. And this here is in electrical degrees, not mechanical degrees. You always want to get in electrical degrees to draw it on the phasor diagrams. Mechanical degrees only helps you know physically what it would look like, but you need to apply then the number of poles, pole pairs. There's a little formula. Here it is, yeah. It's in the formula sheet. Number of apply that formula to actually change from mechanical angle to an electrical angle. We need electrical degrees to draw the phasor diagram, and electrical degrees on this one as well. As we push that torque angle high and high and high, we open the turbine steam valve, we try and drive it more and more and more. We eventually get to a maximum power there, which will correspond to 90 degrees. That means if you have stator, a south pole and a north pole of the stator, the rotor pole will be exactly halfway between the two of them. Yeah. Sorry, I lie.
It'll be at 90 degrees.
Will it be halfway between the two of them? I think it will have actually pushed. I'll have to think about that. It might have actually pushed the north right up to almost going past the south. I'll have to think about it. Doesn't matter. At the end of the day, you can push harder, 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 but eventually you come to a point where you push too hard. And now the torque is actually going down. It's too easy. It's actually kind of pushed to a magnetic, you're pushing hard against magnetic field, and then you kind of pop through the field, so to speak. It's a bad way of describing it. But basically now suddenly you're going to get less torque being produced and less power being produced, which means, how did you get here? You got here by opening the steam valve more and more and more and more. Eventually you get to a point where you open it some more, suddenly actually you can't absorb all that energy into the grid. Meanwhile, the steam valve, because you can't deliver as much power because you can't push as hard, so you've got nothing to push against. So that steam turbine will just accelerate like crazy, and this thing will spin radically faster than the synchronous speed and induce a whole lot of current and blow things up, basically, and some circuit breakers would have to act pretty quickly. So you can't utilize this area here. It's a completely, Ben's going walkabout.
Yeah, I'm just plugging in to the grid.
Okay. You do realize that you do realize that you're going to make some generator somewhere struggle just a little bit harder than it was.
Yeah, not much.
Not notice it. Cool. Okay, so this region over here is somewhat theoretical and is completely what's the word? It's an unstable equilibrium if you did have an equilibrium over here. So you can't use that. And there's a little formula that works out. It's very hard to see it there. I need to zoom in here slightly. You can see it a bit better. I'll scroll over here, but I can drag these very good-looking guys a little bit further up there. The power is E naught times E over XS, but there's a sine theta in the formula somewhere. Not theta, delta, the electrical degrees, the torque angle. So the max occurs when you reach that 90 degrees. So there's an offset of 90 between these poles. Roughly linear for the first 30 degrees or so, and many machines are designed to run rated at about 30 degrees, electrical degrees torque angle. Normally there's less than 30 then on the mechanical angle because there's multiple pairs of poles around the stator. So just a few degrees on the mechanical could mean 30 degrees on the electrical. Okay, so have a look at that one yourself here. This control of active power, they don't go into any detail here about how you would control these things, but they are, I'm sure you know the stories with governors. You dealt with governors?
Yeah.
Okay. So there's things controlling the speed of all of these things, and if they see the speeds are starting to drop, there's some massive control room somewhere which says, start shutting off Auckland, places that are not really necessary like that, drop them off the grid so that we can bounce back. Otherwise, everything starts to slow down or voltages start to dip. So yeah, that's a bit of a
load shedding.
Sorry, some load shedding.
Under frequency load shedding. Yeah.
Yeah, we had some pretty bad time in South Africa a couple of years back where they were load shedding every day in a sort of a cyclical.
Right. Okay.
So each suburb basically of the city, or the whole country, each suburb sort of had 4 hours a day to be off.
Did they not have enough generation?
Yeah, it's a bit of a debate as to whether it was a ploy to get us to be happier to pay higher amounts for our electricity because you're just so glad that it's back and it's stable.
Okay. Political.
Yeah, or whether there really was a lack. I think there was maybe a bit of both. I think the demand certainly was going up, and every now and again they did have to do maintenance on one or other generator somewhere, and then sometimes there wouldn't actually be enough. So they were trying to obviously balance things, and there was always just that it was that evening peak normally was the main thing.
Yeah, right. Okay.
So yeah, there's another whole story as to how to load shed, etc., to try and keep everything balanced, or allow more steam into your turbines to try and handle that extra power. But eventually everything reaches a maximum operating point, and you can't keep pushing it too far. Eventually you reach a pressure or whatever that the thing's not designed to handle, and something has to give. And normally that something is dropping some poor load off the grid unsuspectingly for a time at least, until things come back into equilibrium, and then we can switch them back in. But of course, switching some of these big circuit breakers off once a day for 4 hours and back on again, they're not designed to do that. And of course, a few of them exploded here and there.
All right.
And burnt down the odd substation. So they also realized after a while that wasn't really the best way to demonstrate that people needed to pay more for their electricity. Yeah, so there were a few fires. Anyway, okay, transients reactance, you can cross that off. That's a bit more advanced than we need. So 1622.
That sounds like level 7 stuff.
It does. It does. Yeah. Sounds like stuff that Bojanga should be tackling in electrical machine dynamics.
You've got it. Yeah.
Okay, so we forget about that. Power transfer between two sources. Sounds like too much pain and suffering. Forget about that.
Cool.
Efficiency, power, and size of electrical machines, purely for your own interest, if you want to give that a read. Mm-hmm. Basically, bottom line, big machines, more efficient. Okay, which brings us then straight into the synchronous motors, and we pretty much know the procedure already, but let's have a look. The actual design of the system is much the same. There's a bit on here where, okay, you can't have, there's obviously no generator providing you with torque on this shaft. The torque is coming electrically from the grid. So you wouldn't have the scenario, yeah, okay, you can have that. So the grid is causing the thing to rotate, not some external turbine or something. But you can still have this, you will still have this exciting current changing the field on some kind of a generator over here, which is actually basically like a DC generator. It could be going out through a commutator and then into here via the slip rings, but as they've shown it for here, it's coming out through a no commutator, so it's actually a three-phase generator, a little one. three-phase alternator, they might call it, going through a rectifier, and then that rectified current going through producing the exciting. So remember, this is like the pilot exciter over here. That's a small control current which is changing the flux here, which changes the amount of current induced in this little mini generator, which then changes the amount of exciting current that's fed into the rotor. And that exciting current that's fed in here will determine how much current, or voltage rather, gets induced between the terminals of the three-phase machine. Okay, obviously, technically the speed that you spin this thing also affects the excitation voltage. If you slow the spinning down, you reduce that excitation voltage as well. So that relationship between the exciting current and the exciting voltage is actually for a given speed. But generally speaking, we're talking about fixed speeds, because for generators, definitely, normally you're sitting with your 50 hertz, come what may. For motors, we might have speed controls on these things, so it's not necessarily 50, and there are some equations that look at that, but it's beyond the scope of what we need. Okay, so there's actually a mini generator in here, but that's got to get power from somewhere. Where does it come from? It comes from the shaft. Where does the shaft get its power from? It's actually coming from the grid. So there's an electromagnetic field, obviously, interfacing between the stator and the rotor that's pushing this rotor around. Now it's pushing it around, whereas the turbine was kind of trying to drag it ahead of the rotor. Now the rotor is pushing this thing around, or pushing, pulling, doesn't really matter. And what you're not seeing here, of course, is that there's a load connected to the shaft. So there's a shaft poking out one or other side, and it's turning something, a hoist, a conveyor, a pump, a fan, whatever it might be. But just bear in mind that there's energy extracted out of the shaft to turn the load, and there's also some energy extracted to force this current carrying coil here to turn in this magnetic flux that's provided by this field pole. Because this thing is a generator, it has to be generating current to feed the exciter. Now, it doesn't need much current in theory, because if you make this quite a thin wire with 25 gazillion turns, you just need a couple of amps, because amp turns is the driving force that makes a magnetic flux. So if you have lots of turns, you can have a very small amount of amps. So you can have a relatively low amount of power drawn here from this little mini generator. Remember, because we could be getting this free if we tried hard enough. How do we get it free? We've put a bar magnet in here, a big fat one. It would spin. We don't need any extra power to actually make the magnetic field. But because it's an electromagnet and the magnetic circuit doesn't have, it's not infinitely permeable, you need some amp turns to drive that flux to generate, to establish that flux. You need some MMF, magnetomotive force. So you have to have some current in here, and you have to end up with some R squared R power losses, or volts times amps if you prefer. So there's a little bit of power wasted in here, but the amount of current that this thing carries, and perhaps even the voltage that's feeding it, compared to the voltage that you might have here on the stator, and the stator currents is maybe 100 to 1 or something. So you're only stealing a small fraction of the shaft power to keep this excitation going. And if you had a well-designed machine, it's not going to steal that much. Then, of course, there's also some friction, potentially stealing some of the torque that's produced. And there's also losses in here in terms of R squared R losses in the stator, and there's some magnetic circuit losses in the stator as well, the so-called core losses, like a transformer would have. Okay, so in a situation like this, of course, we're looking at an input over here. This is now an input producing a rotating magnetic flux, and that will then be trying to drag this thing around following it, those attraction and repulsion forces. little bit about starting over here. If you suddenly put 50 hertz on a synchronous machine, its inertia, it's quite heavy generally. Its inertia, the magnetic poles passing, the stator poles passing the rotor poles will pass them so quickly that it won't have time to drag them around and maintain that attraction. Because once it goes past it, you know, if it was attracting it over here, when it goes past it, suddenly it ends up repelling it. So it has to stay in steps, so to speak. There's no steps, it's smooth, but it has to stay in phase, or yeah, let's call it in step. So you have to help this thing up to speed somehow. So you either need to attach another little motor, like an induction motor, onto the shaft, engage it, let it spin this thing up until it's almost reached synchronous frequency, or the speed corresponding to synchronous frequency, and then suddenly remove this motor and engage the stator, bring power onto the stator. So until then, you keep the stator engaged, you just don't provide any excitation. Okay, and then you remove that little motor and then provide the excitation. Alternatively, they discuss it here that you can have an extra winding in the machine, which makes it act like a induction machine. So an extra winding on the rotors so that on the stator, so that you can keep the exciting current off, and you can rely on slippage between the rotor and the stator to induce current, like you would have had for an induction machine. That induced current will form magnetic poles, which will start dragging the rotor around, trying to follow the stator like an induction machine would. And once it gets within a few percent, then you're in a position where you can suddenly apply that exciting current to the rotor. And now it will lock in, suddenly jump in and lock there, and the two will rotate together. So as long as you're going pretty close to the right speed and you time it just right, you can suddenly provide the excitation current and the two will lock in. And once it's locked in, if you did have these windings that would act like an induction motor, those windings now will not see any, there'll be no EMF induced in them, because now the two are rotating together, so you've got no slip. Remember, for an induction machine, you had to have some slip between rotor and the rotating magnetic field to actually get flux cutting the conductors and producing force to drag the thing around. If the two are operating together, moving synchronously, then of course we don't have that flux cutting, and you won't induce any current in those coils. That coil just goes to sleep, and the thing now becomes a synchronous machine. If it's a motor that speeds it up, they call it a pony motor, for no apparent reason. Otherwise, for a big machine, you need those well, you can choose either as to whether one wants an extra motor or to have extra windings in the same motor. If you have the luxury of a speed controller, variable speed drive, you can take the 50 hertz and slow it right down to like 0 hertz and slowly crank it up, so that this thing starts to slowly spin faster and faster. So if you have control over the frequency by like a variable speed drive, variable frequency drive that is, then you can start pretty much at 0 and slowly crank this thing up. And you don't need to have any pony motor or induction windings. But if you're going to throw 50 hertz on it, you're going to have to make a plan. You can read through that about the pull-in torque. That's showing us there how there's a bit of an offset again between the rotor poles and the corresponding opposite poles on the stator, so that now the stator is dragging this thing around. The stator is leading. The south pole of the stator is slightly ahead of the north pole of the rotor. The north pole is trying to catch up all the time while this pole keeps moving. And it keeps moving because we've got this three-phase producing a rotating flux. Okay, so there's a whole bunch of poles which are all lined up relative to each other, and they're staying locked in, but they can be a slight behind or a slight ahead, depending on whether it's in motoring mode or in generating mode. We can stretch it further back or further forward, depending on the torque. Okay, so when we get to analyzing these things, this is where they show we can do this with a bit of a sort of mathematical version, if you like, as opposed to a more geometric version, where we just represent an impedance as, well, a reactance as an impedance of Jx. And Jxi then becomes a voltage. So we've got that relationship directly between the voltage and the current. And so we can construct ourselves some phasor diagrams. You guys are quite good at all that sort of stuff, so I'm not going to bore you. In here, you can just have a look through the book in your own time. But basically, that's the way we normally draw it now, would be that we draw the source, which is the grid on the left. Now we're drawing the machine on the right. There is a bit of a hidden something here that one might not first realize, and when you analyze these vectors closely, if you're visualizing this thing as a sink, which it would be if this was a generator and this was the grid, then you're looking at currents flowing this way with the same, everything else, the same polarities. And your phasor diagrams are drawn bearing in mind that you've got current flowing into this grid in terms of, you know, what's a rise and what's a drop. Current's flowing this way, the voltage vector is the other way. Whereas when you're visualizing this thing now as a motor over here, typically you're visualizing it as if current is coming out of your grid. The voltage vector across this thing is now the other way. So the two phasor diagrams look similar, but there's a bit of a hidden difference in that the one has got the current defined coming out of the grid, the other one's got the current defined coming into the grid, which actually changes the nature of that voltage vector across this thing when you draw the phasor diagram. So you don't see it, but just bear that in mind, because if you just look at this, you'll think to yourself, hang on a minute, I'm seeing current to the right, I'm seeing the voltage vector to the right, regardless of whether this current is slightly below this line, as it is for a motor, or slightly above that line. If I do I times E times cos of that power factor, it would look like you're going to get a positive number. Because both of them are vectors in the same direction. But actually, there's a difference here, because in a way, that current vector is actually kind of opposite. So if we were drawing this same diagram on the same diagram as which we used for the generator, I think this current would actually have to be defined the opposite way. Somewhere there's a 180 degrees switch in the mix, because they've defined the current this way with a corresponding volt drop. And in the other one, it was defined the other way. So both ways, you're seeing a positive number when you multiply R by E. They're in the same direction, and it looks like a positive number, which makes sense. But in the one case, it's a positive amount being fed into the grid, and in the other case, it's a positive amount being extracted out of the grid, in accordance really with the way they've drawn that current direction over there. Of course, these things, it's a bit strange, of course, because we know that this is AC. So these things are changing polarity all the time. Well, in fact, this one's not, is it? That point there is actually the neutral, and we're drawing this per phase, eh? So technically, this one is actually staying zero, if you like. It's the start point. And this one is changing. It's going above the start point and below the start point, above the start point and below the start point. But these arrows, these vectors, give you a snapshot in time. So when this is more positive here, and the current is like that, and this is like this, then we have these vectors. And when it changes, they all change together. So you're really looking at it as a snapshot in time with respect to some sort of datum. Okay, but I think you know all of that sort of stuff. So again, the thing here is dictated by this angle delta, which is electrical degrees, which is to do with how far now is the rotating magnetic field of the stator ahead this time of the induced EMF in the EMF induced in the stator by the rotor. So this one is the E that's provided by the grid. It's feeding into the stator. This one is the E naught that is generated also in the stator by the induction, induced by the current, the rotor current as it sweeps past the poles. But again, it's that difference that actually causes current to flow in that stator. It's a bit complicated in the sense that the stator is seeing two voltages. It's seeing the grid voltage and it's seeing the induced voltage at the same time. They're superimposed, so to speak. And it's that difference which is actually making current flow in that stator. So once we've got those two vectors, again, this one is not necessarily the same size. If this thing was a certain voltage and this one was the same size, we would typically call that neither over nor under excited. It would just be, we'd say it would be the rated amount. Even if they're equal in size though, we'll have this phase shift. That phase shift will cause, when you subtract the one from the other, we'll get that difference. That difference we can visualize over here. So in other words, this vector here is parallel to that vector over there. We're just drawing it head to tail over here. And once you've got that, we know that the current will be perpendicular. So that angle between that and that will be perpendicular because it has to be, because it's a reactance, pure. And once we've got that, we can establish an angle between the E and the I, which is then the power factor. It's the power factor that this thing is running at. The product of I and E will be your apparent power per phase. If you multiply it by cos theta, where theta is this little difference in between there, then you'll have the real power. If you multiply EI by the sine theta, you'll have the reactive power. And of course, all of those, if you want it to the load as a whole, you must simply multiply it by 3, because this is actually analyzed per phase. And this vector here is not the line-to-line voltage, it's the line-to-neutral voltage. And so is the E naught visualized as being induced between line and neutral. Okay, so here all they're doing here is they're putting that little lot in vector notation. They're saying rises equals drops over here, and then they're separating things out into basically when you're adding vectors or phases, it's always good to have them in rectangular format. So that would be your line voltage or your grid voltage, if you like, at 0. That would be the E naught that's being induced by the sweeping rotor. They're telling us that it's happening with a 30-degree electrical lag. So the line is ahead of the rotor, it's dragging it around, it's a motor. But once you've got that naught and that 30, it enables you then to break it down into the rectangular components, the real component and the imaginary component, because this one happens to be, one of them happens to be 0 anyway. Once you've got those components, we can then add things and end up with a number at an angle. Well, first we'll end up, as usual, with the real part and the imaginary part, and you can convert it back to a number with an angle, so that you can actually visualize it as a phasor. So that one there that they found here is EX. So it's this thing here. They found it mathematically. That number then is 50 degrees between there and there, which means that number there is 90 minus 50. So that must be 40 in this case. With me, that 50 is between, that 50 is from the reference phase as 0, which is here, 2EX, that's 50. But from there to there is 90. So this little difference in the corner here must be 90 minus 50. But it will work out for you because when you apply Ohm's law here, you've got I equals V over R, but of course it's not R, it's X. When you're dividing and multiplying numbers, I'm sure you know by now, it's always best not to separate them into their rectangular components, their real and imaginary parts. It's best to leave them in polar format. Because when you divide, you subtract a 90 from a 50 and you get a minus 40. Okay, so when you multiply, you actually end up just adding the numbers that are in the two phases. You add their numbers, but when you divide one by the other, you subtract the bottom one. So you get 50 minus 90, you get minus 40. So that would have just told us there's a 50 there, that leaves 40 over there in this particular case. And once you've got that, you now know where that 40 is telling you between the reference phasor, which happened to be the grid voltage, the grid phasor. So that 40 automatically now is actually the power factor. Cos of 40 is the power factor. There's the line current and there's the line voltage. That difference has to be the power factor. Okay. So we can analyze it like that. You can also do it with the cos rule like we had for the other one. You don't need to do it with these, breaking it up into its components. You can establish this thing using the cos rule or any other trig that you can think of. But all that this thing is doing here is really breaking it into trig using a bit of, cos and sine, breaking things up into horizontal and vertical components. So you can do it in a more sort of a trig approach if you like. And that's almost the end. Where are we? Okay, there you'll see the active power. It's times 3. There's no root 3 in there because we've already got a line to neutral over there. There's already a root 3 in there.
Yeah.
So it's times 3 there. There's a little example to look through here. You can look through this one as well. This one just takes it a few steps further. This one, once you've done that basic phasor diagram to find the main currents and voltages and everything, they're just taking it a step further here by specifying some losses in this case. R squared losses, R squared R losses in the rotor, the stator core loss that's in the actual magnetic circuit of the stator, and windage and friction, which of course is effectively reducing the torque on the shaft because some torque's being used to overcome friction and less torque therefore is available at the end of the shaft driving whatever load there is. So have a look through that one as well. It just shows how we can take the numbers that the vector diagram, phasor diagram is showing us. It's showing us amounts that are input to the stator on the diagram that we just looked at. But then you're going to start to lose a little bit because of these various things.
Yep.
This one here, the R squared R losses for the rotor are supplied by an external DC power, so they don't affect the mechanical power. So they won't come into the calculation for the power available at the shaft. But when you come to work out the efficiency,
electrical efficiency,
yeah, then you need to bear in mind that actually some power is taken from the grid to make that excitation current that you inject into the rotor. So it will appear here as one of the losses because you're looking at the net effect. It's no use, you're looking at net effect, you're taking something out, but you're taking out through the shaft and you're taking a bit extra for that exciting current. Having said that, it depends a little bit. The way that they've shown it here, where there. In this case here, the power is actually being extracted in the form of, there's a torque required to make this current carrying conductor turn in this magnetic flux over here. That of course induces the current which feeds this, and there's the R squared R loss in here. But you can see it coming from, in this case, it's not coming from the grid directly. It's coming via, this thing's making this thing into a motor. The motor's turning. This is like a mini generator turning because the motor's turning, which is generating back into it. So you've got a kind of a motor and generator happening at the same time. But the one's extracting a little bit of power out of the grid, requiring some torque to turn it, and the other one's extracting a whole lot of power. That's the majority of the torque, which would then be going onto the load. Whereas other examples would have slip rings where you would feed the grid's 3 phases, the lines coming into the motor, you'd feed it straight onto the, not straight, you'd take the grid, take the grid supply, 3-phase, you'd rectify it, and there'd be 2 slip rings. And you'd feed that rectified current into this thing via those 2 slip rings. Okay, so in that case, there wouldn't be a little mini generator and either a commutator and slip rings, or a generator and rectifier. You would just feed in current extracted from the grid through a rectifier, through the slip rings, and you wouldn't have this thing at all. Okay, but even if you did that, you'd still taking current from the grid, from the line, to help you. So you do have to subtract it off when you're working out your efficiency. But it won't be seen as a torque on the shaft, whereas this one here would be seen as a torque on the shaft. It would have to cause extra line current to flow in here to generate that extra torque. Okay, so it's a little bit of a difference whether you visualize it as a generator inside there or as current coming in straight from the line. Most small synchronous motors will just have 2 slip rings ready for you, and you just feed your exciting current directly into the slip rings. That's the same as the one that we've got on campus. There's no mini generator inside there generating the exciting current for you while the thing's turning because it's a motor. Okay, so look through that one. And yeah, these funny formulas like that, don't worry to try and learn funny things like that. All that thing is power equals torque times omega. And you've got a synchronous speed happening over here. The 9.55 just comes from a 2 pi
constant, isn't it? Yeah.
Yeah, and it just,
I've seen it before.
Yeah, and where does the 2 pi come from? It comes from if omega equals 2 pi f. And where does the 60 come from? It comes from the conversion of per second to per minute. So you don't need to remember funny formulas like that. You can just go pi equals torque times omega. Again, the 2 are exactly proportional because the speed is fixed, assuming we've got a supply voltage with a fixed frequency.
Yeah.
Okay, there's a bit of discussion here about a thing called reluctance torque versus just the normal attraction. Read it for interest only. A bit more discussion about the relationship between the degrees, the mechanical degrees and the electrical degrees, but it's all just to do with the number of poles or pole pairs. And there's a little bit more reluctance torque, as I say, just know what it is, but no analysis required on that. Losses and efficiency, don't worry about that specifically. Excitation and reactive power, okay, that's worth a read.
Yeah.
Excitation and reactive power. We'll obviously look at this a bit more in our block course anyway, so we'll fine-tune this slightly. But they are discussing here the power factor and how we can actually use this thing by either over-exciting or under-exciting it. we can actually use it even in the motor mode. We can deliver power to the grid, not power, reactive power.
Yeah.
So we can make this thing act as if it was a capacitor. Or we can make it act as, by under-exciting it, we can make it act as if it was an inductor, so that the grid feeds it as if it was an inductor with a lagging power factor. That would be seen as taking reactive power from the grid. And the other way would be providing reactive power to the grid. So if you've got a big factory, you can actually do some power factor correction by having a synchronous motor in there. Because if you overexcite the rotor purposefully, it'll force reactive power into the grid. So some factories do that. Instead of having a whole big bunch of capacitor banks to try and correct the power factor, if they do have synchronous machines available, especially big ones, they can purposefully choose a level of excitation which overexcites them, which actually forces reactive power into the grid. Making the grid see the motor, which is absorbing real power, making it see it as if it was a capacitor in terms of reactive power. And in fact, you can operate this thing so that it's neither a motor nor generator. It's just floating on the line. By simply adjusting the amount of excitation, you can make it act more like a capacitor or more like an inductor by over or under exciting it. So you can make it a synchronous condenser, they call it, which is when it is acting like or synchronous capacitor is another term for it. It's acting like a capacitor, but you can make it act like either. So you actually have 4 quadrants that we'll look at on campus. You've got a real power into the grid or out of the grid, and at the same time, so it's motor, generator or motor, and at the same time you've got reactive power into the grid or out of the grid. So the sort of capacitor versus inductor way of viewing it. So you can have any combination of those. You can have positive real power, negative reactive power, or you can have vice versa, or both positive or both negative. And we'll look at all of those modes in our prac setup on campus and do the whole synchronization thing. V-curves, purely out of interest. Main thing that we're looking at here is that as you adjust the excitation, so you inevitably you end up affecting a little bit of both the reactive power and the real power. So there'll be a specific spot where you've got your rated, this is IX, that's the exciting current. So as you overexcite it, and what is this telling us? It's telling us that, this is real power here. Real power. So the real power is somewhat affected by whether you're overexciting it or underexciting it to some degree. The real power is affected on this curve, but not as much as the reactive power if you overexcite or underexcite. So yeah, don't worry too much about those V curves. This one's normally under is more applicable because you're normally trying to run the motor at or near full load. This one is showing you what's happening under no load, where it's possible to actually have no real power and just reactive power, basically. Okay. So yeah, no calculations, or in fact, even the definition of the V curve, you can leave that out. Which brings us to stopping, and again, this is beyond the scope of our work, but basically, by providing a resistor between the 3-phase resistor between the lines, you can remove the you can disconnect the motor from the grid. You could let it spin there forever, but if you put some resistors between the phases, you'll extract some energy out of there, like you would with a braking resistor with a DC motor. Or if you short circuit those together, you can also cause currents to flow, which will slow the thing down. Eventually, the current has to be given off as heat in the resistor R squared R, either resistor internally in the stator winding, or a combination of the stator resistor internally with whatever resistor you connect physically on the outside of the motor as well. As I said, by then you've disconnected from the line completely. So that'll just slow it down faster. So that's beyond the scope of our course as well. But yeah, slowing down a big machine, it can be necessary to actually put in some resistor bank to allow R squared R heat to be generated, which is then extracting that energy out of the half mv squared essentially of the actual big heavy rotor that's spinning, or the load that's spinning, for that matter. Which brings us to the end. That's worth a read, just the difference between synchronous versus induction. Obviously, most of it stands to reason. Synchronous gives you very precise speed control. It can never be anything different to exactly what the frequency is. But for that reason, of course, if you want to change it, you have to have a speed control. Induction, you can play a little bit with some other parameters to try and get some speed control happening, or even loading up the shaft with torque will try and make it slow down slightly. I think probably the efficiencies can be better synchronous. Induction motor relies a little bit on slip. And as soon as you've got slip, you've got those R squared R losses, which are proportional to slip in the rotor. And you're going to have some inefficiency happening over there. But you can minimize that slip by having a well-designed machine, of course. So yeah, have a read through that. And the synchronous capacity here, yeah, that's just concept only. We're talking about the fact that you don't have to have necessarily a physical load on the shaft. The thing can be spinning freely and providing VARs. Generating VARs, acting like a capacitor, so providing purely reactive power. And that is it. So if you look at the thing I sent, okay, so I'll send out to everybody the final assignment, which has just basically got 2 questions, but essentially it's 3. Question 1 is on generator in isolated load and grid connected. So it's just 2 typical phasor diagrams where we've got a known power factor or a known angle between the E0 and the E, and we work from there. And then there's one similarly for the motor scenario. Now, of course, in the motor scenario, there's normally only one scenario because effectively it's always grid connected. You're supplying it from the grid. So there's only one phasor diagram for the motor, not like the generator where you could have an isolated load or the infinite bus. So that's a separate question for the motor. Also, just revolves around those phasor diagrams. And that's all we need for that 3rd assignment. I'm keeping it a bit shorter and sweeter. Obviously, we'll discuss these things a bit more in class in our block course, and we can revise it a bit more and emphasize a few points and highlight a few things. But basically, that's what you can focus on is those phasor diagrams. Cover it in the assignment. And then, yeah, that's pretty much it, and we'll see you at the block course.
Is that, it's not far away, is it? A couple of weeks.
It's actually, I think, 2 weeks from tomorrow.
Yeah. Wow.
Yeah,
cool.
Next week is the last week of the teaching semester. Then the next week is the first week of exams, and as you said, it's that first Friday, so it's Wednesday, Thursday, Friday that we've got.
Brilliant.
Yeah, so 2 weeks, which means if I dish out the assignment for this tomorrow, and I'll send you just that first question, but I'll include the second one as well, the motor one. If I dish it out tomorrow, then hopefully folk can return it by this time next week. So a week for that one because it's pretty quick, that one. Much shorter than the others. Well, maybe I have to make it the Friday or something. Yeah, then everybody can hopefully come fresh and prepared for the block course.
For sure.
Cool. Okay, I'll give you a date.
Good.
I'll give you a date in Moodle, but it will be it won't be
no stress.
It won't be before that Friday, so it's at least a week and a half. Probably I'll just make it actually early the next week, just before you come for the block course. Maybe the Monday will be good enough to hand in that assignment. Yeah. Okay. Cool.
Okay, Brendan. Thanks for all your online courses this semester. It's been good.
That's a pleasure, and thanks for always being there to have someone to chat to. Talking to oneself would be really, really sad. A little bit scary.
It would be hard for you.
So yeah, thanks a lot. You and Cameron. Cameron obviously couldn't make it tonight.
Yeah, I'll give him a wind up. Right.
Cool.
Thanks, and we'll see you in a couple of weeks.
Cool. Cheers then. Bye.
Okay, bye.